slides.
How are you?
Yeah, good to see you.
Our science session, I had to ask some of the speakers to be a little bit flexible and to try some new things. So we had a couple of submissions that were fairly similar, and I couldn't reject either talk, and so I approached the authors to consider a collaboration. And so we have two of these collaborative talks this afternoon. And this is the first one by Anne Treasure and Katrin Tirok, and they're going to be talking about using R in oceanography.
Okay, can you hear me? Yes? Okay, thank you, Andrew. As Andrew has said, Katrin and I are going to be talking about how we've used R in our oceanographic research. We've both got similar data from similar sampling devices, but we'll explain in our talks what exactly we've done. And then we're going to showcase just different things we've done with the data. So I'm going to show you more of a preliminary stuff, looking at how I've used R mostly with the graphics to spatially visualize my data. And then Katrin will go more into kind of some more analysis and stats. Oopsie. There we go. So I work down in the Southern Ocean, and I use two instruments called Argo floats and instruments that are carried by animals. Sorry, I just keep on going down rather than across. There we go. So just as by way of a brief introduction, why in the Southern Ocean? Well, the Southern Ocean is crucially important to the global ocean and climate system in that, as you can see in that bottom left figure, it connects all the other major oceans in the world. And through this way distributes ocean properties such as biogeochemical pathways and water mass properties and heat and that kind of a thing. But the Southern Ocean it's notoriously it's very difficult to collect data there because it's obviously hard to get to. The logistics are quite difficult and it's expensive. The ice is a problem, rough weather. So for this reason, autonomous devices such as Argo floats have become crucial to to data collection. Argo floats, as I've said, autonomous. You basically just throw them over the side of the ship, and they're programmed to go off for a few years, and they dive up and down, and as they come up, they collect salinity and temperature data, and when they get to the surface, they send the data to the satellites. But obviously, down south, this is difficult because of the ice, so they can't actually get to the surface to talk to the satellites. In summer, the bottom right, that's a picture in the middle of summer, you can see how thick the ice can get. On the surface even then. So the Argo floats are quite limited, particularly south of 60. Advection is also a problem where the floats get advected to the north because of the strong currents. So that's where these little guys come in. These loggers were developed in the early 2000s, and it's quite a mouthful, so I only say it once: the conductivity, temperature, depth, satellite relay data loggers. So I'll just say SEAL CTDs from now. And these are attached to the animals, mostly onto their heads. And then when the animals go out and forage and dive up and down, the temperature and salinity data is collected as they come up. And then when they surface, it gets sent to the satellites. And obviously ice is not as much of a problem for these guys because it's their world, they know what they're doing. And this work is part of that little, you can't really see it, MEOP. It's an international consortium of about 13 countries now. And this is, obviously you can imagine with such a big area, people need to collaborate. So there's this massive data sharing going on. And the database currently got quite a few million data points now, over about 500,000 profiles that these seals have collected. So while studies have used both Argo floats and SEAL CTD data sets, not much is known about how well the two data sets overlap in space and time, and also how they compare in data quality. So the second part of the data quality I won't have time to get to today, but initially I'm just looking at sort of a spatial and temporal overlap. And for this I've used an R package called OCE, which was developed by Dan Kelly and Clark Richards. And these two are really proactive and really active developers of this package, and they've got this GitHub site that if you've got any issues, you post to that, and they're very quick to pick up on any bugs that might happen, and they can put functionality in there that you might want. So that's how we got to this section of the work. First of all, it wasn't really projecting the Antarctic polar projection properly, so we fixed that bug. I say we, they fixed that bug. And then the problem with what I wanted to do was plot data density distribution, so the density here just being the number of profiles per unit area. But the problem here is to go from long lat space to XY space, in that the closer you get to the poles, your long lat boxes decrease in size. So you need to normalize this somehow so that you can compare your densities with area. So that's what we did through this whole issue on GitHub. And with the OS functions of map plotting and the color maps that they've got, we went through all sorts of iterations of plots and finally came out with these, which I was very happy with. And if you look inside the black circles, you can clearly see that south of 60, the density of the seal profiles is much higher than it is for Argo. And this is what we would have expected. Sorry, it's getting cut off a bit there. Here we go. ggplot also shows it really nicely. You can see with the overlaid histogram that very clearly south of 60, the seals dominate with the profiles, and Argo peters out to almost zero quite quickly. Another little layer that you can add with ggplot is showing the total in the background, which is another interesting way of looking at the data. And then if you split it a bit more into seasons, just doing a simple density plot in the base package of stats. And the interesting thing to take from this is that there's more of a marked difference in winter. Sorry. And you can see that the seals utilize south of 60 more in the winter than they do in summer. And this has very important implications for data collection in winter when you have no other way of actually getting down to the ice and under the ice. A little bit more functionality with OS, that's quite useful. It's got this function read Argo, and as its name says, it reads Argo files, but the seal CTD files are formatted in the same way. So read Argo, you can read those files in the same way, and then you can do interesting things like just plotting. This is a single seal track. It's a South African seal, and each point shows one profile, one dive, just to get an idea in long lat space of where your seals are. The summary of an Argo object here just shows the normal things. It's got a few extra interesting things that are quite useful to know. It's also got these interesting functions that are useful, a handle flags function. Your Argo files have data quality flags, and you can select which data you want. It's on a scale of 1 to 9. So using handle flags, you can kick out some flags, keep other flags, and then you can grid it to get to your regular pressure levels. And then again, using the image and color map functions of OS, you can pull out section plots of what you're interested in. So I'm mostly interested in with the temperature and salinity with latitude to see how it changes. And again, this is just for a single track, a single dive. Obviously, you'd use a lot more, but I'm just showing one here for an example. Work in progress now for the second part of the study, which I'm not going to get to today, is now to take this data, the temperature and salinity data, and to use those to identify characteristics and properties of fronts, such as the subantarctic front and the polar front, which is what I'm mostly interested in, and to see how the seals compare to Argo, and in the places where Argo can't get in the wintertime or under the ice, how are the seals doing to actually plug that gap. And that's all I have time for. It's your... It's this one, yeah. All the way to the top, please. Why does it do two? It should one page. Can you change the setting? Probably view. Okay. All right. Thanks, Anne, for the introduction to ocean data in general. So I just want to show some. You can't hear this. Okay, I didn't know that. Just thought it's my fault. Okay, is it better now? Okay, great. Okay, I have to.
I don't like this. I can take this off. Okay, that's better. Yeah, I'm Katrin. I'm from Durban, UKZN, and I just want to present two short examples of some plots I did with some ocean data, more on the R side. I try to keep it on the R side, not so much on the scientific side actually. And I work with data from a glider mission, so that's a so-called glider. It's also an autonomous underwater vehicle, so it dives autonomously and takes similar data than Anne was talking about, so-called CTD profiles, so conductivity, temperature, and depth profiles. And we deployed such a glider just off Sodwana Bay here in the northeast coast of South Africa, in the coastal areas. And after some pre-processing of the data, which come in binary format if you load them off the glider, I was able to read them into R, and then I can use a package called Gibbs Seawater Library, which is also part of the OCE package, to calculate some further seawater characteristics like salinity, density, things like that. But the question is then, when I have that, where can I go to get like some graphs, maybe for publication and so on. So I just want to show you an example here of temperature data. So the glider takes pretty much follows 1/3 tracks. So I have, kind of a sheet in the space, so I can just plot them on 2 dimension here over the depth and the distance of the glider track. And the data were quite irregular, so I couldn't put them in a matrix or anything like the raw data. So I used a scatter plot, so GM point, and used ggplot, and used temperature for the color, and then used R color brewer and scale color gradient to define my scale from dark blue to red for low to high temperature. That worked pretty nice, but I can see that I have quite a few gaps in the data, like here, 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 and so on. So for further for discussion or publication of the data, I rather want to have a picture like that, nice homogeneous picture. So I have to do some kind of interpolation. There are lots of different methods, linear interpolation, splines. We decided to do some creaching, so-called creaching. It's a geostatistical method that considers distance and degree of variation between known data points when estimating unknown data points. So it's based on a spatial correlation model, so-called variogram. And the packages I used, mainly the GStat package, which offers a broad functionality for spatial-temporal geostatistical modeling, prediction, and simulation, and also function from the SP package, which is a package for classes and methods for spatial data. And the first step to do for that, you have to build, or you have to calculate that spatial model, the variogram. I used the function variogram here. So you have to give your formula temperature dependent of distance and depth in that case, and then I get that picture, and then I can fit a variogram model using the function VGM, which pretty much describes 2 parameters, the flatten here, which is called the sill, and then at the distance it flattens, called the range. So I put those in the model, get my model, which is the base for the creaching. And then the next step is to define the spatial grid onto which I want to interpolate the data. I use the function expand grid for that one. And then I can do the creaching interpolation using the function creach, where again I define my formula here, temperature dependent on distance and depth, give my data grid I just defined and the model, the spatial model I defined, and then I can get my result, so my creach data, which I can plot on my graph again. And the advantage of using creaching over like some other interpolation methods is that I also get an error or variance of my creached values, of my interpolated values. So I can see here the yellow and red values are higher variance. So in the regions where I had no data or very few data, of course I have a higher variance of my estimated values. But yeah. So that worked quite nice, and I can do that as well for salinity and other variables I have. The second thing I want to show is, so the glider also gives information about water velocity when it takes the dives. It's the average water velocity over the depth. And it was particularly interesting for us because we dropped the glider here in the warm Argallis current, which comes down at the east coast of South Africa. Unfortunately, not all the way down to Cape Town. So Durban has this nice warm water. Cape Town is just ice cold. I don't get it, but anyway, that's the Argallis current, which brings us this nice warm water. And it's a very powerful current, so we wanted to know like the velocities and plot them on a nice map. So the velocities come as x and y components of a vector. I just showed a table here, and then of course I have the GPS coordinates, and I used ggplot and geom segment to just plot the line segments, giving the coordinates, and the arrow function to make it a vector. Works quite nice. But now I wanted to have that one on a map. So I used the package ggmap, which is really great. It's also by Hadley. And it works seamlessly together with ggplot. So I pretty liked that when I discovered it. And there's a function get map, and one can just put in like a location. You can just type in a word. So for example, if you do that for Cape Town, you get this map of Cape Town, in that case from Google Maps, on a specific zoom level. But of course, you can also put in your own coordinates and choose a different map type. So I chose satellite for my purpose, and then just combined it with the geosegment function I did before, and then I get my velocities of the water, of the current here, nicely on the map. And then I just added, like marked my smallest velocities in green and my highest ones in red, things like that. And added some labeling, of course, and some scaling, and got a really nice picture for my purpose to maybe put in a publication or something. Yeah, that's about all I wanted to tell you today. So in summary, using R for processing data from ocean sciences works pretty well, and we get this package OCE, which is very good for certain data. Unfortunately, they don't have a real tool for glider data, like for the Argo float, you get that function. Unfortunately, they don't have that to load in raw glider data, so I had to do some pre-processing in MATLAB, actually, unfortunately. But nevertheless, maybe it still comes. But yeah, there are all these other R packages who are just great to do the visualizations and further analysis, of course, GStat for geostatistics. And yeah, overall, oceanography is still very MATLAB focused, and I just discussed. So we hopefully in future more oceanographers will also go for R, and we get more shared code out there. All right, thanks for your attention.
So we have time for a couple of questions. Sorry. I find this work, sorry, let's turn that on.
Cool, thanks. I find this work very interesting, and it's a shame that, it's the first time we're actually seeing this. So you guys, do you run like blog, do you post these kinds of things, or experiment? Because you seem to sort of face some problems, or not challenges that I was facing in plotting and sort of experimental thinking. Yeah, so do you guys share it, or?
Amongst ourselves probably, but yeah, not really with blogs. I don't know if you...
I actually aim to maybe make more use of GitHub and stuff, but I don't run a blog, so I'm usually too lazy for these things. Really sorry, but I think I will maybe just, upload some stuff. I do.
Another question? I have a completely unrelated question, but I was just wondering, unrelated to R, but the gliders, do you retrieve them?
Yeah, of course. They're ridiculously expensive. Although I think sometimes they also lose them. So we had actually a glider that came out, was shipped out from the States, because we collaborated with some people in the States, and they shipped them all over the world and deployed them and then collected. So we collected them, the glider, just after a few days, because it got it got into the Agulhas current I showed, so which is really fast. So that's Sodwana Bay for those who know, and down here is Richards Bay. That's where we collected the glider, and it took like 5 days to get down from there. So it was really fast, and we had actually to kind of go a bit sooner because we didn't want it to interfere with any ships coming closer to Durban, and it was kind of a pilot project. So, but no, of course they get retrieved.